0 to 80% state of charge in under 5 minutes. If you're into EVs or frontier tech, you know that sentence is basically the holy grail. It's the moment electric charging stops being a lifestyle and starts being a normal Tuesday. And for years, we've been promised the magic solution will be solid-state batteries. Lighter, safer, faster. The kind of tech that gets announced every year, like a new miracle diet, but for electrons. So Donut Lab just dropped a video series called I Donut Believe. 10 out of 10 name, no notes. And this first episode isn't just marketing slides. It points to an independent customer report produced by VTT, document VTT-CR-00092-26, dated February 9th, 2026. The report is essentially a lab write-up showing extreme fast charging on a single Donut solid-state battery V1 cell. It's not a pack-in-a-car test. It's not a lifetime test. It's not a safety abuse test. It's a very specific question. How fast can this cell charge, and how hot does it get when you try? So today we're going to keep the hype on a short leash, keep the physics on a long leash, and see what this report actually proves, what it doesn't prove, and what the next receipts need to be if Donut wants people to take production vehicle claims seriously. Chapter 1. The cell, the setup, and the 4.3 volt overdrive. All right, what did VTT actually test? One cell, customer supplied. The report describes it as something the customer identified as a solid-state battery cell. That's an important detail. VTT is not doing a chemistry teardown here. They're not certifying the internal materials. They're testing the behavior of the device they were given. If you hear someone say, VTT proved its solid state, that's not what this report is. Now, this is also not some microscopic coin cell party trick. The report lists the cell as roughly 26 amp hours at a nominal 3.6 volts, about 94 watt hours. That's a meaningful chunk of energy. Not an EV pack, obviously, but also not a science fair battery taped to a potato. The whole test is intentionally simple and a little brutal. They run two passive cooling setups, one with two passive aluminum heat sinks, one on each side, lightly clamped, mainly to provide a heat path, and one with only a single heat sink on the bottom. Basically, let's make cooling worse and see what happens. No liquid cooling, no active temperature control, just raw metal and consequences. Then they do a baseline capacity check with a standard discharge cycle. And after that, they hit it with two ridiculous charge rates, 5C and 11C. Quick translation. C rate is a way to normalize charge speed. 1C means a full charge in 1 hour. 5C is, in theory, full in about 12 minutes. 11C is, in theory, full in about 5 to 6 minutes. 11C is not fast charging. That's, we're trying to force electrons through the door like they're late for boarding. Now here's another key technical detail. The fast charge protocol uses a maximum charge voltage of 4.3 volts. The report also notes the recommended upper end of the cell's usual charge window is 4.15 volts. So yes, this is performance forward. You can call it overdrive. It absolutely helps you cram charge in faster, but it may also increase stress. Whether that matters depends on the thing nobody has shown yet, long-term cycling data. Okay, what were the actual results? At 5C, 130 amps, the cell reached 80% state of charge in about 9.5 minutes. At 11C, 286 amps, it reached 80% state of charge in roughly 4.6 to 4.9 minutes. So yes, the under 5 minutes to 80% claim for this cell under this protocol is supported by the VTT timing tables. That's the good news. Chapter 2: The Thermal Twist and the Efficiency Tax. Now for the part where physics sends you an invoice. Fast charging is a heat story. The report measures surface temperature, not internal core temperature, so keep that in mind. Surface temperature can understate what's happening inside, especially during violent charge events. Still, the surface numbers alone are spicy. At 5 degrees Celsius, with the two-sided heat sinks, surface temperature peaked around 47 degrees Celsius. With only one heat sink, it peaked around 61.5 degrees Celsius. At 11 degrees Celsius, with two heat sinks, surface temperature peaked around 63 degrees Celsius. With only one heat sink, it hit about 89 degrees Celsius. And here's the line that matters. The first attempt at the worst cooling 11C test was interrupted because the cell hit the 90 degrees Celsius safety limit. VTT stopped the run, let it cool, and later improved contact to continue. So when Donut says bad cooling is actually pretty good for our cell, here's the truth hidden inside the marketing. Yes, sometimes a warmer cell has lower internal resistance, so its voltage rises more slowly, so it can stay in the constant current phase longer, which makes the charge event a bit faster. But that's like saying driving downhill makes your car go faster. True. Also, the cliff is still there. If your comfort zone is flirting with 90 degrees Celsius on the surface, your real question is not, can it do it once? The real question is, what does that do to degradation? What does that do to safety margins? What does that do after hundreds of cycles? Now let's talk efficiency, because it's one of the quietest and most important signals in the whole report. At their slower reference cycle, the round-trip energy efficiency is roughly 92%. At 5C, it drops into the mid-80% range. At 11C, it drops to roughly 82 to 83%. That missing energy doesn't evaporate, it becomes heat. And that's why fast charge at scale isn't just a battery story, it's a thermal system story. Cooling plates, coolant loops, bus bars, connector design, charger design, and yes, the grid. Module 3, Chapter 3, Megawatt Math and the Ultra-Fast Charge Club. Here's the zoom out moment. At 11C, one cell can see peak electrical power north of a kilowatt during these charge events. Scale that into a vehicle pack, and minutes to full stops being a chemistry flex and starts being an infrastructure flex. You don't need the exact number to understand the point. Once you scale this to an EV pack, the limiting factor becomes whether you can deliver megawatt-class power safely and whether you can move the resulting heat out of the pack without cooking it. Now, how does this compare to other batteries? Mainstream lithium-ion cells, what most EVs use, are generally designed around modest charge rates for longevity. EV fast charging in the real world is often limited by thermal management and the CC to CV curve. The last 20% slows down dramatically because that's how constant voltage charging works. That's why 0 to 80% is always the celebrity metric. The final 20% is the awkward part where the charger turns into a polite drizzle. Then there's lithium titanate, LTO, the old guard of the ultra-fast charge club. LTO can charge insanely fast and last forever, but usually trades energy density. It's the marathon runner chemistry, not the lightest, but it will not die. And there are also high-rate LFP pack claims that brag about big, range added in 10 minutes numbers. Those are pack-level claims heavily dependent on thermal design and pack architecture, not just raw cell behavior. Where Donut lands, based on this report, is simple: ultra-fast charge acceptance. This is real evidence that this cell can take extreme charge rates. But staying in the club requires more than one impressive run. Chapter 3: Megawatt Math and the Ultra-Fast Charge Club. Here's the zoom out moment. At 11C, one cell can see peak electrical power north of a kilowatt during these charge events. Scale that into a vehicle pack and minutes to full stops being a chemistry flex and starts being an infrastructure flex. You don't need the exact number to understand the point. Once you scale this to an EV pack, the limiting factor becomes whether you can deliver megawatt class power safely and whether you can move the resulting heat out of the pack without cooking it. Now, how does this compare to other batteries? Mainstream lithium-ion cells, what most EVs use, are generally designed around modest charge rates for longevity. EV fast charging in the real world is often limited by thermal management and the C to CV curve. The last 20% slows down dramatically because that's how constant voltage charging works. That's why 0 to 80% is always the celebrity metric. The final 20% is the awkward part, where the charger turns into a polite drizzle. Then there's lithium titanate, LTO, the old guard of the ultra-fast charge club. LTO can charge insanely fast and last forever, but usually trades energy density. It's the marathon runner chemistry. Not the lightest, but it will not die. And there are also high-rate LFP pack claims that brag about big range added in 10 minutes numbers. Those are pack-level claims heavily dependent on thermal design and pack architecture, not just raw cell behavior. Where Donut lands, based on this report, is simple: ultra-fast charge acceptance. This is real evidence that this cell can take extreme charge rates. But staying in the club requires more than one impressive run. Chapter 4: The Missing Receipts Scoreboard and what comes next. This report proves one thing exceptionally well: fast charge acceptance under passive heatsink setups. It does not prove the rest of what people actually care about. So here's the Missing Receipts Scoreboard, the things you need before revolution is a responsible word. First, cycle life. Can it do this 5-minute 0 to 80 charge 50 times? 500 times? 1,000 times? Show the capacity retention curve under 5C and 11C protocols. Second, calendar aging. What happens when the cell sits at high state of charge in heat for months? Third, safety abuse testing. If you puncture it, crush it, dead short it, overcharge it, or heat it from the outside, what happens? Solid-state marketing often leans on safer. Cool. Prove it with abuse tests. Fourth, energy density and dimensions. People are trying to compute watt-hours per kilogram by eyeballing a YouTube video like it's a crime scene documentary. Listen, you cannot compute weight per kilogram from vibes. The report gives no mass and no dimensions for the tested unit, so density is unknown from this document. Fifth, module and pack behavior. Even if the cell is great, packs introduce new demons: hotspots, gradients, balancing, current distribution, packaging overhead, and cooling complexity. Sixth, repeatability and manufacturing variance. This was one cell. One. That's a good start. It's not a production claim. Now, Donut is framing this as a series, And that's actually good news, because the smart move is to use the next drops to fill in the scoreboard. Donut Lab has said these results will be released in a series, and their site shows the next drop scheduled for Monday, March 2nd, 2026 at 1500 Finland time. If they're smart, the next receipts are either cycle life, safety abuse, or hard density numbers, mass and dimensions. Because right now, what we have is a very impressive stunt with real third-party data behind it. And stunts are great. A revolution is when the stunt still works on the 500th try, with boring safety margins in a real module with real manufacturing. So here's the balanced take. This VTT report is meaningful evidence that this donut cell can accept extreme charge rates, fast enough to hit the under 5 minutes to 80% headline under specific conditions. It is not evidence that it's ready to replace every lithium-ion pack on Earth. Not yet. The right posture is curious but disciplined. Enjoy the wow. Track the receipts. And remember, the future always arrives as a spreadsheet first. Osiris Perseus is about exploring modern topics from breakthroughs to other foundations of science, tech, and engineering. Subscribe to join the expedition.